think we can start our session. It looks like it's already 10 minutes past 11. And the speaker of this is Dr. Michael Yatauro.
Yatauro.
From Penn State University, Brandywine campus. And joint work with 4 other people. And I would appreciate if you could recognize your co-authors.
Oh, yes, certainly. Well, thank you all.
And the topic is Vertex degrees, binding number, and factors.
Yes, thank you. Well, thank you all for being in attendance. And yes, I would like to acknowledge my co-authors here, Douglas Bauer, his grad student Ori Navo, Ed Schmeichel of San Jose State, and of course Douglas Woodall of Nottingham, so University of Nottingham. If you're familiar with binding numbers, you may recognize Douglas Woodall as one of the foremost authorities on the binding number. So it was a pleasure, and it's been a pleasure to work with him. So Vertex degrees, binding numbers, and factors. So essentially we're going to be combining the notion of the degree sequence with a bound on a binding number of a graph to determine results concerning factors. So some preliminaries. So we have here, we're going to consider finite undirected simple graphs. We're going to denote graphical sequences or degree sequences by pi or pi prime if we have multiple to refer to. The degrees will be listed in non-decreasing order from smallest to largest, and then a finite sequence pi is graphical if there exists a graph having pi as its degree sequence, and such a graph is called a realization. For example, here is a specified degree sequence 2223333, or in the alternate notation with exponents to indicate the number of times that degree appears. The realizations are not unique. These two are clearly different realizations because one is disconnected, the other is connected. So that would be a graphical sequence. P-theorems. So we're going to let P be a graph property. In particular, we're going to be concerning ourselves with increasing graph properties, meaning that if the property exists for the graph, then adding edges will preserve that property. So for the purpose of this talk, graph property will always refer to increasing. So Hamiltonian, K-connected, for example. Okay, so a graphical sequence pi is forcibly P if it happens that all realizations possess that property P. And we're going to be talking about what are known as P-theorems. We may say forcibly P-theorems or just simply P-theorems, which are theorems that use conditions on the degrees to guarantee the property P. So these will be sufficient conditions. As far as being forcibly connected, for example, this graphical sequence is not because it does have a disconnected realization. Okay, so we're going to introduce the notion of a best monotone theorem beginning with Kvattel's theorem for Hamiltonicity. Basically, if we check these roughly n over 2 implications by looking at the degree sequence, if the sequence itself satisfies all of these conditions, then every realization of pi will have a Hamiltonian cycle. We're going to talk about some properties that the theorem possesses and then identify the notion of best monotone. In particular, if given 2 graphical sequences, or just any n sequences of the same length, we say that pi prime majorizes pi if pi prime is term by term greater than or equal to the entries of pi. Here's an example of a pi prime majorizing a pi. And then a p-theorem is monotone increasing, or for us we'll simply say monotone, if whenever it declares a graphical sequence to have the property p, then every majorizing sequence will also be forcibly p as well. So Kvattel's theorem, it turns out, is monotone. Given a graphical sequence that satisfies the conditions of Kvattel's theorem, any larger sequence will also satisfy these conditions and be forcibly p as well. Okay, so we're going to be focused actually primarily on the notion of weak optimality. So a p-theorem is optimal if whenever it fails the conditions of the theorem, then the graphical sequence itself has a realization without that property. But we're not going to focus on optimal, we're going to focus on weak optimality. Weakly optimal means that if the degree sequence or graphical sequence fails to satisfy the conditions, then it might be that all the realizations of pi have the property, But what we're interested in is that there exists a majorizing sequence that has a realization without that property. So the majorizing sequence in question is not forcibly P. We can prove that Kvatl's theorem is weakly optimal by looking at if it fails for any I. Essentially, we have these two inequalities are satisfied. And it turns out that if you just make the first I degrees I, and then the next n minus 2I, the n minus I minus 1, and then there's no restriction on the remaining degrees, you make them all n minus 1, then this sequence pi prime is guaranteed to majorize pi under these conditions. And we can look at pi prime, it does have a realization that is non-Hamiltonian. So pi fails, there is a majorizing sequence with a non-Hamiltonian realization. In fact, this realization is not even one tough, which is necessary for Hamiltonicity. Okay, so we're going to focus on what we mean by a best monotone P-theorem. So given a P-theorem T naught, we call it best monotone if it is monotone and weakly optimal. And what we mean by best monotone is the following theorem, that if T naught is monotone and weakly optimal, then we have the following result. Given any other monotone P-theorem T, if T declares pi to be forcibly P, then so will T naught. So in a sense, T naught is the best monotone theorem for that property, in that the set of graphical sequence that T declares forcibly P is a subset of those that T naught will declare forcibly P. And Kvatl's theorem is best monotone because it's both monotone and weakly optimal. So usually we check the monotonicity is not that difficult to observe. And then the weak optimality, once that's verified, we know that we have in our hands a best monotone theorem for that property. So I'm going to combine the notion of setting restrictions or conditions on the degrees, just as Kvatl's theorem does, with also assuming a bound on the binding number. Now, what do we mean by the binding number of a graph? So bind of G, we look at all the vertex subsets that are non-empty and whose neighbor set is not the entire set of vertices. And then we take these ratios of the neighbor set of X divided by, well, the size of the neighbor set divided by the size of the set. Look at all those ratios, the minimum is the binding number. So for example, this bow tie graph has binding number 4/3. We can get a minimum such ratio if we consider these three circled vertices where the neighbor set is everything but the upper right vertex. So we get 4 neighbors and 3 vertices, we get 4/3 is that ratio. So what I'd like to do now is I'm just going to essentially present a survey of some recent results concerning when we have conditions on the degrees. What if we take into account that we know the binding number is at least 1, and we're only interested in the 1 binding realizations, and we want to guarantee that those realizations have the specified property. So we're going to consider factors, 1 factors, i.e. perfect matchings, or 2 factors. In particular, a Hamiltonian cycle is a special case of a 2-factor. So in some sense, what we're looking at is we're looking at the best possible way of combining the understanding of the binding number is at least 1 with conditions on the degrees to guarantee the specified property. So these will be, in some sense, the weakest conditions necessary on the degrees if you happen to know the graph is 1 binding. And it turns out that the binding number of a graph can be determined in polynomial time. So if you're interested in just 1 binding realizations, we can find that with relative ease. There is an algorithm for that due to Cunningham. Okay, so 1 binding, I should mention 1 binding means that the binding number is at least 1. Okay, so what I'm going to do now is I'm going to interweave. I'm going to say here's the best monotone theorem for a property, and here's what it looks like if we're only considering the 1 binding realizations. Here's Kvatl's again. It is best monotone for Hamiltonicity. So we have a result here that's in some sense a 1 binding relaxation. If we know the binding number is 1 and we want to impose conditions to guarantee Hamiltonicity, it turns out that the first set of conditions here look exactly like the conditions for Kvatl's theorem. And then we have this additional set of implications to check if n is odd. And then if all of these collectively are true, then every 1 binding realization of pi is Hamiltonian. It turns out that if n is even, we get no relaxation because Kvatl is just these conditions if n is even. But if n is odd, then this 1b collection of implications replaces the quatal implication, which is essentially reduced to this inequality, where when you get about halfway through the degree sequence, all the degrees have to be more than half the number of vertices. So this is actually relaxed in that you may not need those degrees to be bigger than half the number of vertices until later in the degree sequence, if you know the graph is one binding and n is odd. Okay, so we're going to have some theorems concerning perfect matchings, but in particular, best monotone theorem for deficiency. The deficiency of a graph G is the number of vertices unmatched under a maximum matching. So we call a graph G beta deficient if the deficiency is less than or equal to beta. So there are most beta vertices unmatched under a maximum matching. And we have this theorem is actually best monotone for deficiency. So if n is congruent to beta mod 2, then we have these somewhat similar implications to the quatal conditions dependent on beta. If all of these are correct and true for the given sequence, then pi is forcibly beta deficient. All of the realizations will have deficiency at most beta. So we're just going to look at two special cases. In particular, just to give you a quick verification, that theorem is weakly optimal if you have that the sequence pi fails for a particular I, then we essentially have these two inequalities. We can build this sequence pi prime that majorizes pi, and then this realization G prime of pi prime has deficiency beta plus 2. In particular, if you were trying to find a maximum matching, you would have to match these I plus 1 isolates, as many as possible, to this clique down here, and you would have beta plus 1 left over of these isolates, so they would get unmatched. And then here, because n and beta are congruent mod 2, this component is always odd. So if you try to find a maximum matching in this component, you're always going to miss one, so you miss beta plus 2. Okay, so the deficiency of that larger sequence's realization is greater than beta. So it is weakly optimal. In particular, for a one factor, if you set beta equal to 0, you get this corresponding theorem. Okay, every realization has a one factor if n is even. There's this, I wasn't involved in this relaxation, but if we're only interested in one binding realizations, then these are the conditions. If n is even and we want the one binding realizations to contain a one factor, we have this collection of implications to check, and then this additional pair, this inequality or that inequality. Then for deficiency 1, if beta equals 1, then we can convert that theorem to the following conditions. Okay, just plugging in beta equals 1. So in some sense, if n is odd, the best maximum matching would leave one vertex isolated in the matching. So it turns out that if we're only interested in one binding realization, so if at the outset we know that our particular graph is one binding and we want to know conditions on the degree sequence that would guarantee deficiency 1, this is what they would look like. In fact, these first two here are exactly the same as the one factor, and then we have this additional inequality to check in the antecedent. And then here, the consequent is a little bit modified because now we have 3 parameters, I, j, and k, to work with. So we have some extra conditions to check, and then these two inequalities in addition to that, if n is bigger than or equal to 13. So all the one binding realizations will have deficiency 1. Now concerning two factors, well, there is this nice result. I really do like this. I wasn't involved with this project, but Bauer and his colleagues here, as usual suspects, as they call, as he refers to them. We have here, this paper presents a result where under these conditions, pi forcibly contains a two-factor. So we have to check all these individual conditions. If they're all true, then every realization of the graphical sequence will have a two-factor. So recently I just looked at it and thought, well, what happens if I'm only interested in the one binding realizations? It turns out that the conditions B through D remain exactly the same. But in this first condition, when n is odd, we do get a somewhat slight relaxation on the conditions required for the degree sequence. So again, even when n is even, the theorem is identical. When n is odd, we get a slight relaxation in the first condition. Okay. So there we are. With Hamiltonian cycles, one factors, deficiency 1. When we have a 2-factor, right, we can get a slight relaxation when n is odd to guarantee every one binding realization contains a 2-factor. You might wonder, well, why one binding? What if we want the binding number to be bigger than or equal to some number between 1 and 3/2? For example, because usually once we get beyond 3/2, then you've got Hamiltonicity and 2 factors and so forth. So we pushed b a little bit bigger than 1, and then just tried to answer the question of Hamiltonicity. We came up with this conjecture. Okay? The conjecture is that if the graphical sequence satisfies all of these beautiful conditions, very easy to digest conditions, then every b binding realization, every realization with binding number at least b, will be Hamiltonian. We checked it, and when b is 3/2, these are all vacuous, because 3/2 should guarantee Hamiltonicity for the binding number. Well, we were able to prove that guarantees 1/2, which is necessary for Hamiltonicity, but we weren't able to get far enough. Okay, so to conclude, I'm sort of doing the press junket here in some sense. Interested in learning more, we have a survey paper that's generating some interest on best monotone theorems. Various colleagues, Doug Bauer, Heiko Boersma, Jan Van den Heuvel, Nate Kale, Ori Navel, and Rich Michael, Douglas R. Woodall, and myself. You can learn about underlying theory, best monotone theorems for other properties, the notion of improving theorems in a best monotone sense, and much more. Okay. Found in graphs and combinatorics. So thank you for your time.
Any questions or comments?
Oh, this way here? No, that Douglas Woodall is very good at checking the minute details of things. He'll even notice if we accidentally italicize a semicolon somewhere where it should have been, in standard font, because it doesn't match accordingly in the rest of the text. So he's very good to have as a co-author.
Any other? So we start our next talk within 1 minute.
No.
Thanks.